Good morning, and thank you very much, Paul, for a great talk. And I'm hoping to build on some of the ideas that he presented. But the talk I'll give today represents a collaboration between myself, Joanne Morgan, Peter Wright, and Adrian Reinsdorf. And this work was really stimulated and enhanced by discussions that we had at the recent Aberdeen workshop. So it's very much a work in progress. I hope that when it's finally done and dusted, it doesn't deviate too much from what I'll present today, but what you're seeing is very much is a first cut at our attempt to answer this question: how does the reproductive rate of commercial fish scale with size composition? Okay, we've heard in particular Mark's keynote address, but also again in Paul's keynote address, that for management the sticking point is the perception that by switching from total egg production, you'll be adding in more noise than signal. So this is a key stumbling block for implementation of information about stock reproductive potential. If you look at how we calculate total egg production, it does have more terms, more biological terms in it, usually through the addition of something like the sex ratio, because of course the fecundity term is somewhat aligned with the weight term in spawning stock biomass. But from a stock assessment point of view, this formulation of stock reproductive potential is regarded de facto as having more noise than spawning stock biomass. And if you compare the spawning stock biomass formulation, this has fewer terms and less noise. Now, the situation is somewhat paradoxical, as Mark really pointed out, because many of the ICES assessments of SSB assume that weights and maturities are constant over time. So I don't know quite how they can reconcile that with not adding signal. They're deliberately avoiding signal. So having this perception that total egg production introduces noise is somewhat inconsistent with how they actually go about estimating spawning stock biomass. But this is the key stumbling block, I think, for implementation. So it's something that we'd like to address in this talk. Now, as Paul pointed out, the underlying assumption about stock dynamics is that the total egg production scales in proportion to spawning stock biomass. This is equivalent to saying that the population relative fecundity, that is total egg production divided by spawning stock biomass, is constant and doesn't vary over time. So this term A is what I'll subsequently refer to as population relative fecundity. It's directly analogous to relative fecundity that we calculate at the individual level, that would be fecundity divided by total body weight. So it has units, number of eggs produced per unit grams. So this population level fecundity is really a reflection of the productivity levels of the stock. So the assumption that this value is constant over time is really an assumption that needs to be definitively tested so that we can see whether or not spawning stock biomass is appropriate. So we can test this theoretically, and I'm really going to build on Paul's presentation in the next few slides, because this assumption that the population relative fecundity is constant is entirely dependent on the condition that fecundity scales linearly with body weight, such that the exponent in the power equation is 1. So Paul already covered that ground, thankfully, which allows me to save time. But if you recall, it's cropped up in different guises and in a variety of talks that we've heard at this symposium. So I think it's lurking in the background, and it's a very important assumption to examine in close detail. So I'm going to use the figure that you saw in Paul's presentation that built on a PhD thesis by E.J. Dick, and he was looking at rockfish. And as Paul pointed out, you can see that the posterior distributions of the parameter B are in considerable excess of the expectation of 1. So the value 1 is indicated by the vertical solid line. And in fact, if you can see a dashed solid line to the right, that is the overall median, and that's a value of 1.35. So there's certainly support here for the fact that the exponent is in considerable excess of 1, and I'm going to use the value 1.35 to see what the implications of that are. So if we resume our sort of theoretical approach here, we can see, okay, there should be some analogous relationship between population relative fecundity, that is TEP divided by SSB, and individual relative fecundity, that is individual fecundity divided by individual body weight. So if we now plug in our power equation for individual fecundity that has the exponent 1.35, you can sort of do the math, and on the variety of this basis of this relatively straightforward calculation, you can develop a relationship between population relative fecundity and body length. There is the expectation that population relative fecundity should scale, in this case, linearly with length. So in fact, on theoretical basis, we can reject the assumption at the population level that relative fecundity is constant and invariant, and accept an alternative hypothesis that it in fact scales with length. Well, the great thing is we've got heaps of empirical data to test this as well. We've got a theoretical expectation. Does it hold water when we test it, challenge it with data? And largely as the result of scientists who are engaged with fresh, we now have some lovely, highly resolved TEP time series that we can bring to bear on this question. So we have these long time series of TEP, plus we've got the time series of SSB from the conventional assessment reports. And the stocks that you're going to see in this presentation include Barents Sea cod, 3NO cod, 3LNO American plaice, North Sea haddock, and North Sea plaice. And when I say these are biologically very well resolved, it's because they're drawing in empirical data from long-term monitoring programs and the particular life history traits that they've resolved very well and to varying degrees are year-specific maturity. In many cases, there's been an ability to resolve year-specific fecundity via adding in the effect of interannual variation in condition. And we've also got sex ratio information, and that sex ratio can deviate quite considerably and often in relation to length. So many of these time series, of course, are now published, so we can really build on this work and test this hypothesis in a reasonable amount of detail. Okay, so that's what we did for all these 5 stocks, is calculate the ratio of total egg production divided by spawning stock biomass, which is population relative fecundity, and what do you get? If you calculate the mean length of spawners, so that's on the x-axis, and it is the mean length of the spawning stock biomass, it's indicative of the size composition of the stock in a given year, and you plot that against the population relative fecundity for these different stocks, you see that each stock has a sort of cluster of points. So obviously they are on different magnitudes, and we see to the far right, we see the 2 cod stocks represented. They are larger body sizes, so greater mean lengths compared to the other stocks. You can see that there's a considerable amount of year-to-year variation introduced by things like the sex ratio and the fecundity terms and things like that. But overall, there is evidence of a positive relationship within a given stock. So to make it somewhat easier to look at in a comparative sort of way, we can divide these time series by the overall mean for the time series and standardize it to see what it looks like. And so this is the rescaled version of that plot, such that they are all on a standardized scale, standardized by the mean. And you can see that relative fecundity runs from negative values. You could say that it's in the vicinity of minus 50% to plus 50%. So there's about a 100% deviation here. There is a clear scaling with length of spawner, although individually there's, for the individual stocks, there's a fair amount of noise, but I think it's immediately clear that population relative fecundity is scaling with length. The one thing you could consider is whether or not there are differences among the stocks in the length. And of course, that's an aspect we'll look at in future analysis, whether the slope of the relationship varies according to the value of the B exponent, for example. So I think that there's a lot of detail to be examined yet in this result. But we see clear evidence, clear support for that theoretical expectation that population relative fecundity will scale with length. So if spawning stock biomass is systematically misrepresenting the impact of size composition on recruitment, then we could speculate that there's going to be some knock-on effects to the residuals of the stock-recruit relationship. So that's the next aspect to look at. Now, I used the two stocks with the longest time series for this analysis. That was Northeast Arctic cod and North Sea plaice. And both of these two stocks exhibited very large amplitude variation in mean length of spawner over their time series. So we see this, we can see this sort of lilac shaded area. That's where you have larger than average mean length of the spawning stock and positive residuals. And then the pale blue area is lower than average mean length of spawners and negative residuals. So there would be an expectation of an overall positive relationship in the residuals from the stock recruit relationship. You can see that there is very equivocal evidence of a positive relationship, and you know, if you look at these types of things often enough, you can draw your own opinion basically as whether there is a signal there or not. This is the same plot for North Sea plaice. Again, it's very equivocal in whether or not there's support for the idea when the spawning stock is shifted towards larger spawners, you have positive residuals. So it's not clear whether this impact is translating through to the stock recruit curve, although it is clearly impacting the productivity of the individual stocks. I'd just like to point out a plot that we're very familiar with. It's a publication by Gudrun Martinsdottir in 1998, and at the beginning of the NAFO working group, of course, we were very much taken up with this plot. And what it is the relationship between recruitment of Icelandic cod and the Shannon diversity index. So that's on the lower panel. On the x-axis is the diversity index. She calculated as age diversity, but diversity indices are trying to capture size composition of the stock. So my mean length of spawners is directly analogous to diversity index on the basis of either age or size. So I think that this type of analysis has clear implications to these types of investigations, in that we can think of them as reflecting potentially the same underlying process, that is a differential productivity of large fish compared to small fish. So are we adding signal or noise by switching from total egg, from SSB to total egg production? I think it's fairly clear that, in fact, it's inarguable that on a both theoretical basis and empirical basis, we're adding signal. Total egg production is sensitive to the impact of variation in length composition on stock reproductive potential. And by comparison, spawning stock biomass has a systematic bias that overrepresents stock reproductive potential when the stock is shifted to smaller sizes. And of course, fishing mortality has the negative consequence of shifting your stocks to smaller sizes. So in fact, the quality of the signal in SSB deteriorates as the status of the stock declines. And that's certainly a theme that has popped up again and again in many of the presentations that we've heard over the past few days. I'd just like to mention a few of the processes that cause shifts in mean length of spawners. Of course, it's not just fishing that causes shifts in size composition. It's been speculated that fisheries-induced evolution could impact growth rates, and this would have knock-on effects to size composition of the stock. The one impact I'd like to mention briefly is the impact of warming temperatures, because in some stocks that can cause fast early growth and lower L infinity, so asymptotic lengths. And a PhD student of mine, Alan Baudron, noted that for haddock. And I'd just like to spend the next slide showing some of his further results. So he was encouraged by the result for haddock, which showed a decline in the L infinity values. So he went into the ICES databases and calculated the growth curves for 8 different species. And then further, he got data at the Aberdeen workshop for the flatfish species for Madryn rhinesort. Now, these are plotted by cohort, and what it represents on the y-axis is a standardized L infinity value. Now, this is a combination of demersal, pelagic, and flatfish species. So these species have different growth rates, different life history traits, different generation times. But you can see there's a coordinated and synchronous shift towards lower L infinity values. So in the North Sea as a whole, the commercial fish species appeared to have a decline in their size composition. So in conclusion, population relative fecundity scales positive with the length of spawner. This is true by definition, but there's also empirical support. Spawning stock biomass doesn't capture house size truncation, reduces the reproductive rate of the stock, and well-resolved estimates of total egg production contain more signal than spawning stock biomass. So I think this is very nice for very data-rich stocks, but even if you had a data-poor stock, you could use mean length of spawners as a metric of reproductive rate on the basis of this result. So future work will include adding more stocks that have very high-quality TDP time series, and there's 4 more to go in. And we'd like to link it to the magnitude and direction in time trends in size truncation for the ICES stock. So I'd just like to close by acknowledging the people who've helped along the way, Alan Baudron for sharing some of his PhD data, and then Paul Spencer for lots of things, including answering email very quickly, and Fran Sabarito-Ray for virtually everything. So thank you very much.